Hello, I'm Soyoung Yoon from Seoul National University. I'll present AcuRank Uncertainty-Aware Adaptive Computation for List-Wise Re-ranking, a framework that allocates LLM re-ranking compute based on uncertainty rather than on a fixed schedule. Re-ranking is central to modern search and RAG pipelines, but LLM list-wise re-ranking, which is done by prompting the language model to reorder given passages based on the relevancy to the given query, is expensive and constrained by input length. On doing so, existing approaches are limited to allocate the same compute to every query, which leads to overcomputing on easy ones and undercomputing on hard ones, and fails to leverage the intermediate signals. Our question: when query difficulty and document distributions vary, why should computation remain fixed? We can divide sorting mechanisms of list-wise re-ranking into two popular ideas, which is sliding windows and tournament sort. They all follow the predetermined path, which ways compute for simple cases, can miss difficult cases, and ignore intermediate signals. The core issue is scheduling computation without considering uncertainty in the ranking. Therefore, we propose AcuRank. AcuRank models each document's relevance as a Gaussian distribution with mu as the current score and variance sigma as the uncertainty using a Bayesian true-scale view. We estimate the probability that a document belongs in the top K and only send the uncertain borderline documents to the LLM. After each pass, we update beliefs and repeat, so compute is focused where it is needed most. For example, suppose we have three documents, D1, D2, and D3. D1 has high mu but low sigma, meaning that they have high relevance scores with confidence. In contrast, D2 has so-so relevance scores but has high uncertainty. We select only those documents like D2 on the next round and do the re-ranking. We exclude the already confident ones within this blue area, and keep refining the belief for documents that lay on the gray area. The pipeline in 5 steps. First, initialize mu from the first stage retrieval scores and set sigma with a prior. Second, select candidates whose top K probability lies in an epsilon band around the decision boundary. Third, partition selected documents into groups. Fourth, re-rank each group list-wise and update true-scale scores. Lastly, stop when the number of uncertainty documents fall below a certain threshold. The plots show how probability mass concentrates as we refine. We compare against sliding window, denoted as SWX, tournament sort, and a true-scale static baseline across track DL 19 till 23 and DL hard and bare tasks like COVID and if corpus signal verbose and Sci-fact. We pair multiple retrievers like BM25, Splade, and Contriver with various LLM re-rankers to test generalizability. On the accuracy efficiency Pareto curve, AcuRank variants, denoted as the blue ones, consistently lie on or dominate the frontier across budget levels, exceeding higher NDCG at 10 with the same number of re-ranker calls. In short, we reach target quality with less compute. To verify adaptivity, we correlate calls with query difficulty measured by weighted information gain. We find a negative Spearman correlation with a very low p-value. This concludes that AcuRank automatically spends more compute on harder, ambiguous queries and saves compute on easy ones. This is the main table of our result. Across track DL and bare, AcuRank improves NDCG at 10 while using fewer or comparable calls. For example, AcuRank 9 scores higher than the sliding window with Pascalon, using about 9 calls, and AcuRank with 19.7 calls scores higher than TourRank 10 using 130 calls for sliding windows with third iteration that uses 27 calls. The gains are consistent across different retriever re-ranker pairings, indicating the method is model agnostic. Because we only forward uncertain candidates, the average number of candidate documents can be fewer than the maximum window size. Therefore, we can gain efficiency other than the number of calls. Under similar re-ranker calls, we also observed substantial system-level savings, up to 33% lower latency, and 30% fewer flops, while maintaining accuracy thanks to adaptive selection and early stopping without sacrificing NDCG at 10. To summarize, listwise re-ranking using fixed schedules ignore difficulty and distribution, causing inefficiency. By reallocating compute using uncertainty feedback, AcuRank pushes the parent to frontier, higher NDCG at 10 with fewer or equal calls, and notable reductions in input lengths, latency, and flops. Implementation details and code are linked here. Thank you for your attention.